Make your Python search find the right documents. By the end, you will have a tiny search pipeline you can run in a few lines. You will see how tokenization, stopword filtering, and stemming change what matches. You will also get a simple TF-IDF re-ranker, so results make more sense by importance. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. Search often fails because text is messy. You might have punctuation, mixed case, and many filler words. Success means that top results actually contain the idea a user asked for, not just incidental words. Tokenization, stopword removal, and stemming are the classic, fast way to turn messy documents into comparable bags of words. Compared to dense embeddings, this approach is simpler, easier to debug, and cheaper to run. But it can miss deep semantic paraphrases that embeddings might catch. At its heart, the idea is simple. Tokenization splits text into words so we can count and compare them. Stopwords remove common function words that add noise. Stemming reduces related word forms to a shared base, so plural and tense do not block matches. As a tiny example, imagine 3 short sentences about a quick fox and playful dogs. After tokenization and filtering, we keep words like quick, fox, dog. After stemming, foxes and fox become the same token. That boosts recall when queries and documents use different inflections. We will build a tiny corpus, show tokenization, filter stopwords, do a simple count-based ranking, add stemming to improve recall, and finish with a TF-IDF weighted score that ranks by importance. This snippet tokenizes one document into lowercase word tokens. It creates a tiny 3-sentence corpus for the demo. A regex extracts runs of letters while ignoring punctuation, and lower makes everything case consistent for matching. The code uses re.findAll, which returns the matching substrings as a plain Python list, and assigns that list to the variable tok. Finally, it prints tok, so you can see exactly what the tokenizer produced. The printed list confirms we have clean, uniform tokens ready for later filtering and matching. Next, we will remove common filler words so content words stand out. This example removes common stop words to focus on content words. The snippet defines stop as a small set of frequent function words that rarely help retrieval. It tokenizes the first document and uses a list comprehension to filter out any token that appears in stop, keeping only informative terms. Using a set for stop makes membership checks fast and clear. The snippet prints the filtered list, which is noticeably shorter and more meaningful for search. That printed list shows the core content that will actually help distinguish documents in later ranking steps. Now we will rank documents by simple shared terms to see baseline retrieval. This code ranks documents by how many query terms they contain. It builds DT, the tokenized and stopword filtered version of each document in the small corpus. The query consists of the words quick and fox, and for each document, the code counts how many of these query terms appear. It then sorts the documents by descending match count with a secondary sort by index to keep ties deterministic. The printed top pairs show which documents match the most query terms. This is a first, simple ranking that is fast and interpretable but treats all matches equally. Next, we add a simple stemmer so inflected words match their base forms. This snippet adds stemming so inflected forms match their base terms. It defines stem as a tiny regex-based reducer that strips common suffixes to unify variations, like dogs to dog and leaping to leap. The snippet creates DTS by stemming every token in each document after stopword removal. For the query terms leaping and dogs, the code stems on the fly and then counts matches per document, sorting to rank results. The output shows improved recall because documents that used dogs or leaping in different forms now match the normalized query. Changing how aggressive the stemmer is would trade precision for recall. Finally, we will weight matches by how rare the terms are across the corpus. This snippet weights matches with IDF to produce a simple TF-IDF score. It computes IDFs for the query terms over the stemmed corpus DTs using a smooth log formula, which downweights terms that appear in many documents. Each document score sums term frequencies times their IDF, and the snippet rounds scores to 2 decimals for readability. Sorting by score and returning the top tuple gives the best document and its weight according to this tiny baseline. If a term appears in more documents, its IDF value drops, reducing that term's impact on the final ranking and favoring more distinctive terms. Recap in 3 short points. First, tokenization, stopword removal, and stemming turn raw text into comparable tokens. Second, use this when you need a fast, interpretable search baseline for small to medium collections. Third, caveat. It is vulnerable to meaning changes and will miss semantic matches that embedding models can catch. Next step, tune the TF-IDF stage by adding n-grams and experimenting with the TF-IDF smoothing parameters, or scale the pipeline with an approximate nearest neighbor index for faster searches at larger sizes. If practical, hands-on IR helps. Subscribe and watch the rest of the IR series.